Hello dear students, welcome to mathematics class. This is Prakash from Tunga Degree College, Jamkandi. So in this class, let us discuss some examples on lower and upper Riemann integrals and also integrable functions. So here it is the first example. If f is defined on the closed interval 0, 1 by f of x equal to x for all x belongs to the closed interval 0, 1, then f belongs to R of the closed interval 0, 1. It means that we need to prove that f is R integrable. F belongs to R of 0, 1 means f is R integrable, and also we need to find the value of the common integral, that is integration over 0, 1 f of x dx equal to 1 by 2. This we need to prove for this example. So here the given function is f of x equal to x and the interval is 0, 1. Now first of all we need to divide the given interval into n equal parts. So let p is equal to, so already we know how to divide the given interval into n equal parts, that is the first value, that is 0 as it is because that is the x naught, then x1 that is equal to 0 plus 1 by n, then 0 plus 2 by n and so on, 0 plus r minus 1 by n, 0 plus r by n and so on, 0 plus n by n, which is equal to 1. So here this is because we know that if the closed interval I is equal to ab, then we can divide this interval into n equal parts such that p is equal to, that is the first point, x naught equal to a, then the next point is given by a plus b minus a divided by n. So it is x1, then x2, that is a plus 2 times b minus a divided by n and so on, a plus r minus 1 times b minus a divided by n. So it is the rth subinterval, then a plus r times b minus a by n and so on. The last point is a plus n times b minus a divided by n, this one will give the value as b, which is equal to xn. So here it is the way to divide the given interval into n equal parts. So by using this we have divided the given interval 0, 1 into n equal parts. The first point is 0, that is a, in place of a we have 0 and in place of b it is 1. Then a plus b minus a by n, here it is a equal to 0 plus b minus a, that is 1 minus 0 divided by n. Then a plus 2 times b minus a, b minus a is equal to 1, then becomes 2 by n and so on. Here a plus r minus 1 times b minus a by n is there, a is equal to 0, then r minus 1 into 1 because b minus a is 1 divided by n, and similarly 0 plus r by n and it is 0 plus n by n, which is equal to 1. The first point of the partition must be the lower limit of the interval and the last point of the partition must be upper limit of the interval. So therefore this is our partition. So therefore it implies that now p is equal to 0, 1 by n, 2 by n and so on, r minus 1 by n, r by n and so on, n by n, which is equal to 1. So therefore this one is the partition for the given interval 0, 1. Now consider the rth subinterval. Now for any subinterval IR, for any subinterval IR which is given by r minus 1 by n to r by n, that is xr minus 1 to xr, where r takes the values from 1 to n. Now we need to find the supremum and infimum of the function for this interval. So here the given function is f of x equal to x, then the supremum is, since the function is increasing, then we can find the supremum of the function by substituting upper limit of this interval into the given function. Here the upper limit is r by n and the given function is f of x equal to x. So, if you put x equal to r by n, then the supremum is equal to r by n and the infimum, that is small mr, that is equal to r minus 1 by n, because by substituting the lower limit of the interval we get small mr is equal to r minus 1 by n. Now, and the length of the interval delta r, that is r by n minus r minus 1 by n. So, this is equal to 1 by n, that is the length of rth sub interval. Now, by using supremum, infimum and the length of the interval, we can find upper Riemann sum and lower Riemann sum. So, first let us find the upper Riemann sum, that is UPF, that is equal to summation over r is equal to 1 to n capital Mr into delta r, where capital Mr is the supremum of that interval. Now, it is equal to summation over r is equal to 1 to n. So, capital Mr is r by n and delta r is 1 by n. Now, it is equal to summation over r is equal to 1 to n r divided by n square. So, here we are applying summation for the variable r, but n is constant as compared to r. So, therefore, we can write this one as 1 divided by n square summation over r is equal to 1 to n r. So, therefore, it is our result. Then here it is equal to 1 divided by n square, then this summation over r is equal to 1 to n of r is equal to 1 by putting r is equal to 1 plus 2 plus 3 and so on up to n. So, therefore, this is the UPF, that is 1 by n square into 1 plus 2 plus 3 so on up to n. So, here we know that this sum 1 plus 2 plus 3 plus up to n can be given by, or it is the sum of first n natural numbers, and also we know the formula to find the sum of first n natural numbers. So, here this can be written as UPF is equal to 1 divided by n square and the sum is 1 plus 2 plus 3 up to n. Then this is equal to 1 divided by n square into n plus 1 divided by 2. So, therefore, n into n plus 1 divided by 2 is the sum of first n natural numbers. So, therefore, that is 1 by n square n into n plus 1 divided by 2, and on simplifying we get n plus 1 divided by 2n, because here n and n will get cancelled, then remaining n plus 1 by 2n. So, this is the UPF, and similarly we can find LPF. So, LPF is equal to summation over r is equal to 1 to n small mr into delta r. This is equal to summation over r is equal to 1 to n, small mr is r minus 1 divided by n and delta r is 1 by n. Now, it is equal to 1 by n square, n into n square, and it is constant taking out of the summation, then remaining summation over r equal to 1 to n r minus 1. Now, here it is equal to 1 divided by n square, and this summation can be written in the form of expansion as by putting r equal to 1, 2, 3 and so on. If you put r is equal to 1, we get 0, then for 2 1 and for 3 it is 2 and so on. If you put r is equal to n, then we get n minus 1. So, therefore, it is equal to 1 by n square into 1 plus 2 plus 3 so on up to n minus 1. It is the result. Now, here in the previous UPF, that was the sum of first n natural numbers, but here it is the sum of first n minus 1 natural numbers. So therefore, in the formula n into n plus 1 by 2, we need to substitute n equal to n minus 1. So therefore, we get 1 divided by n square into n minus 1 into n divided by 2, which is equal to n minus 1 divided by 2n, because n and n will get cancelled, remaining n minus 1 by 2n is the LPF and n plus 1 by 2n is the UPF. So therefore, we got UPF as n plus 1 by 2n and LPF as n minus 1 by 2n. Now, to prove the function f is R integrable, we need to prove that lower Riemann integral and upper Riemann integrals are same. For that, first let us find the lower Riemann integral and upper Riemann integral. So here lower Riemann integral is given by integration over bar 0 to 1 f of x dx, because the interval for integration is 0 to 1, and for lower Riemann integral we need to put the bar for the lower limit of the integration, that is bar 0 to 1 f of x dx, and by definition we can write this one as supremum of Lpf, where P is the partition of the closed interval AB. So therefore, it is the definition for this lower Riemann integral, that is the supremum of Lpf, and to find the supremum we are applying the limit as n tending to infinity, because here this lower Riemann integral means that is the area below the given curve or bounded by x axis and the given function. So therefore, here if you are increasing the number of intervals in the partition to infinity, then we can get the exact area bounded by that curve. So that is why we are applying the limit as n tends to infinity, where n is the number of intervals in the partition. If the number of intervals is infinity, then we can get the appropriate area or exact area. So that is why limit as n tends to infinity. Now here LPF is n minus 1 divided by 2n, that is the LPF which is calculated already, that LPF is n minus 1 by 2n. So therefore, now substitute the same LPF, that is n minus 1 by 2n, and we need to solve this limit. Whenever n is tending to infinity, then we need to take that n common. So therefore, that is equal to limit as n tends to infinity. Let us take n common in the numerator, then n into 1 minus 1 by n divided by 2n. We are taking that n common in the numerator, then n and n is get cancelled, then remaining limit as n tends to infinity 1 minus 1 by n whole divided by 2. Now if you put the limit as n tending to infinity, this 1 by n becomes 0, because 1 by infinity is 0. So therefore, we get the value as 1 by 2. So therefore, bar 0 to 1 f of x is x dx is equal to 1 by 2. So it is the lower Riemann integral for the given function, that is bar 0 to 1 f of x, which is x dx is equal to 1 by 2. Next we need to find the upper Riemann integral. So upper Riemann integral is given by integration over 0 to 1 bar f of x dx, where 1 is the upper limit in the interval of integration. So 0 to 1 bar f of x dx, which is given by infimum of UPF. The upper Riemann integral is the infimum of all upper sums, that is UPF, where P is the partition of the closed interval AB. Now here also we are applying the limit as n tends to infinity, means we are dividing the interval AB into n equal parts, and if the number of intervals is more, then we can get the exact area of the given curve. So therefore, it is limit as n tends to infinity, UPF is n plus 1 divided by 2n, and it is equal to limit as n tends to infinity by taking n common, it is n into 1 plus 1 by n whole divided by 2n, and n get cancelled, then limit as n tends to infinity 1 plus 1 by n whole divided by 2, and after applying the limit as n tends to infinity, it becomes that 1 by n becomes 0, then remaining 1 by 2. So, therefore, here it implies that bar 0 to 1 f of x dx is equal to 1 by 2, and also 0 to 1 bar f of x dx is 1 by 2. So, on comparing, we can say that these two are equal. So, therefore, it implies that integration over 0 bar 0 to 1 f of x dx is equal to integration over 0 to 1 bar f of x dx is equal to 1 by 2. So, therefore, here lower Riemann integral and upper Riemann integral are one and the same, then it implies that f of x equal to x is R integrable in the interval 0 1 or f belongs to R of 0 1. So, it is a symbolic representation of the function which is R integrable. So, therefore, f of x equal to x is R integrable in the interval 0 1, and so therefore, that belongs to R of 0 1. And also it is given that what is the common value of the integral. If these two integrals are same, then whatever the value of them is called as common value of the Riemann integral. Therefore, integration over 0 to 1 f of x dx is equal to 1 by 2, and in place of f of x you can put x. So, therefore, it implies that integration over 0 1 x into dx is equal to 1 by 2. So, therefore, it is the answer for our question. Here we have proved that f is R integrable, and also we found the value of that common integral which is equal to 1 by 2. The next example is, show that f of x equal to 2x plus 1 is R integrable on the interval 1 2, and integration over 1 to 2 2x plus 1 dx is equal to 4. It is also similar to the previous example only. Here also we need to prove that the given function f of x equal to 2x plus 1 is R integrable in the closed interval 1 2, and the common value of that integral is equal to 4. Let us solve this one. Let p is equal to 1, 1 plus 1 by n, 1 plus 2 by n, and so on 1 plus r minus 1 by n, 1 plus r by n, and so on up to 1 plus n by n, which is equal to 2, be any partition of the closed interval 1 2. So, therefore, here p is the partition. The points are 1, 1 plus 1 by n, 1 plus 2 by n, and so on up to 1 plus r minus 1 by n, and so on 1 plus n by n. Here n by n equal to 1, then 1 plus 1 equal to 2. That is the upper limit of the given interval. For any sub interval IR, which is given by 1 plus r minus 1 by n to 1 plus r by n, where r takes the values from 1 to n. So, it is the rth sub interval. Now, to show that f is R integrable, we need to find the upper Riemann integral and lower Riemann integral. For them, UPF and LPF are necessary. So, to find the UPF and LPF, we need to find the supremum and infimum for the rth sub interval. So, therefore, here capital MR is equal to, so this supremum can be obtained by substituting the upper limit of the given interval into the given function. So, here the given function is 2x plus 1, now substitute x equal to r by n. So, therefore, this one is 2 times 1 plus r by n plus 1, that is 2x plus 1, where x equal to the upper limit, that is 1 plus r by n. So therefore, this one is equal to 2 plus 2r by n plus 1, which is equal to, here 2 plus 1 is 3 plus 2 times r by n. So therefore, this is the supremum of the rth sub interval, and similarly we can find the infimum, that is small r. To find the infimum, we need to substitute the lower limit of the interval into the given function, that is 2 times 1 plus r minus 1 by n plus 1, 2x plus 1, where x equal to the lower limit of the interval, then it is 2 plus 2 times r minus 1 by n plus 1, which is equal to 3 plus 2 times r minus 1 by n. So therefore, these are the supremum and infimum of the given interval. Then the length of the interval is upper limit, that is 1 plus r by n minus lower limit, that is 1 plus r minus 1 by n. So therefore, this one is equal to 1 by n, that is the length of rth sub interval. Now let us find Lpf and Upf. So now Lpf is equal to summation over r is equal to 1 to n small mr into delta r, and this one is equal to small mr is 3 plus 2 times r minus 1 by n, 3 plus 2 times r minus 1 by n into delta r is 1 by n, and this can be written as summation over r is equal to 1 to n. Now multiplying this 1 by n to both the terms separately, then it becomes 3 by n plus 2 times r minus 1 by n square. Now we can apply the summation separately. So it implies that summation over r is equal to 1 to n 3 by n plus summation over r is equal to 1 to n 2 times r minus 1. Now this one is equal to, here the denominator is n square, 2 times r minus 1 by n square. Now in both the terms we can get that 1 by n constant from the summation, here 3 is also constant. So therefore we can take that 3 by n common, outside the summation, and here 2 by n square is constant, we can write that out of the summation. Then it is 3 by n into summation over r is equal to 1 to n, here it is 1, plus 2 by n square summation over r is equal to 1 to n r minus 1. So therefore it is equal to, here it is 3 by n. Now here it is 1, but the summation is from r equal to 1 to n, means we are adding this one n times, then we get n plus 2 by n square, and here this summation over r is equal to 1 to n, r minus 1 is there. So therefore this becomes, if you put r equal to 1, that is 0 plus 1 plus 2 and so on up to n minus 1. So already we know the formula to find the sum of first n natural numbers, but here the number of terms is n minus 1. So therefore it is 1 plus 2 up to n minus 1. The total sum is n into n plus 1 by 2, but here n equal to n minus 1, then we can substitute that n equal to n minus 1 in that formula. So therefore it becomes, so here Lpf is equal to 3 by n into n plus 2 by n square, and it is 0 plus 1 plus 2 up to n minus 1 is there. Then it is equal to, here n and n get cancelled, it is 3, then 2 by n square, and its sum is given by n into n minus 1 by 2. So then here it is 2 and 2 get cancelled, n and n get cancelled, remaining 3 plus n minus 1 by n, and this we can write separately as 3 plus n by n minus 1 by n. So, therefore, it is 3 plus 1 minus 1 by n, which is equal to 4 minus 1 by n, that is the LPF. And similarly, we can find UPF. So, here UPF is summation over r is equal to 1 to n capital MR into delta r, where capital MR is the supremum of the rth sub interval. So, here summation over r is equal to 1 to n and the supremum is 3 plus 2 times r divided by n into delta r is 1 by n. So, therefore, this can be written as summation over r is equal to 1 to n 3 by n plus 2 r by n square by multiplying each term by 1 by n. Now, apply the summation separately, then it becomes summation over r is equal to 1 to n 3 by n plus summation over r is equal to 1 to n 2 by n square into r. Then here UPF is equal to, here 3 by n is constant, taking outside 3 by n summation over r is equal to 1 to n, here it will be 1 plus 2 by n square summation over r is equal to 1 to n r, then it is equal to 3 by n into. So, this becomes n because we are adding 1 n times. So, therefore, that becomes n, then 2 by n square, here it becomes 1 plus 2 plus 3 up to n because r is taking the values from 1 to n. So, therefore, it becomes 1 plus 2 plus 3 up to n. Now, it is equal to n and n get cancelled, here 3 is remaining plus 2 by n square and its sum is given by n into n plus 1 by 2, 2 to get cancelled, n and n get cancelled, remaining 3 plus n plus 1 divided by n, and this can be written as 3 plus n by n plus 1 by n by dividing n separately. So, therefore, it is 3 plus 1 plus 1 by n, which is equal to 4 plus 1 by n. So, here the upper sum is 4 plus 1 by n and the lower sum is 4 minus 1 by n. Then let us find the upper Riemann integral and lower Riemann integral. So, upper Riemann integral is given by integration over 1 to 2 bar f of x dx, integration over 1 to 2 bar f of x dx, which is equal to infimum of all the upper sums, where P is the partition of the closed interval AB. Now, to find infimum and supremum, we need to apply the limit as n tending to infinity. Limit as n tends to infinity, upper sum is 4 plus 1 by n. So, therefore, if you apply the limit as n tending to infinity, this 1 by n becomes 0, then remaining 4, and the lower Riemann integral bar 1 to 2 f of x dx, that is the supremum of lower sums, supremum of LPF, where P belongs to the partition of AB. Then here limit as n tends to infinity 4 minus 1 by n, that lower Riemann sum is 4 minus 1 by n. Then after applying the limit we get 4 because 1 by n is there, that becomes 0. So, therefore, here we can write that upper Riemann integral and lower Riemann integral are same. Here bar 1 to 2 f of x is 2x plus 1 dx is equal to 1 to 2 bar 2x plus 1 dx is equal to 4. So, here lower Riemann integral and upper Riemann integral are giving the same value, which is equal to 4. So, therefore, the common value of the integral, integration over 1 to 2 2x plus 1 dx is equal to 4. Here we are not actually integrating the function, but we are finding the value of the given definite integral. Here you can cross verify the answer by integrating this 2x plus 1, then substituting the limits 1 to 2. Now, it implies that f of x is equal to 2x plus 1 is R integrable on the interval 1 to 2, or it implies that f belongs to R of 1 to 2. So, therefore, it is our conclusion. So, here f is R integrable and its common value is given by integration of 1 to 2 f of x dx is equal to 4.